which will be focused on AI engines. We want to show them how you can program these devices through our open source technology. Gan will take over and he will give a practical example, then also show some of the applications that we actually already mapped to this hardware. And then Ali will take over and he will talk more about precision data types and why they are important and how you can exploit them on these architectures. Just to set the stage while we're getting started. My first slide is going to be an invitation for creativity, cross-disciplinary, because I think you all know that to be able to support modern workloads become more and more heavy and more data dominated. You need good hardware for that, but that is only one aspect. And so good hardware these days means that you do not only need to be heterogeneous, you don't only need to have multiple cores, you need to make sure that you can specialize certain parts of your chips to certain parts of the workload. So, are we done? Thank you. We're good? Yes. Thank you. Okay, so this is our creativity invitation, cross-disciplinary. So this is a slide we kind of borrowed from Hennessy and Patterson. It shows a story from the it shows a story from the hardware point of view, and they call it the golden age for computer architecture. They call it like that because a lot of innovation needs to go in to make sure that we have actually good hardware able to or be ready to support those very demanding workloads. But that's only part of the story. That's why we call it a cross-disciplinary creativity invitation. You also need your software stack, and you also need good application programmers or designers to be able to harvest the best of the capabilities of these heterogeneous architectures. Today, we're going to focus on a specific part of such a heterogeneous architecture. The device that you see here, the chip architecture that you see here, is an example of such a heterogeneous architecture. It's a Ryzen AI processor. More specifically, it's a Phoenix device. In red, you can see a CPU complex. On top of that, you can see a CPU complex. Then there is some hardware acceleration for peripherals. There are some multimedia engines. But the part we want to focus on today in this talk is on the AI engines. The neural processing unit is an array of AI engines, and we call that spatial compute hardware. Now, to be able to explain to you what spatial compute hardware actually mean, we first want to make a kind of retro-style comparison to the real world. So this is a fictitious story. AMD does not have a warehouse that is that big with overdue paperwork. But suppose that is the setting, and suppose that the problem at hand is that you need to get rid of that overdue paperwork. What we do is we try to find a specialized worker, a paperwork cruncher, that will help us to get through that overdue paperwork. And we equip them, of course, with the necessary means, including a personal message board where he or she can receive the task at hand, what they need to do to process the paperwork. And that stack of papers on their desk, we label it L1. That is a local stack of papers that they will focus on. There's a whole bunch of paperwork overdue, so we need a good set of workers to crunch through this. Please note the spatial configuration of the workers in this real-world example. We group them in groups of 4. That is because, first of all, they like to be focused. They focus on their own paperwork, but from time to time, it might be that they have to sneak and look into some paperwork of their neighbors. And now you most likely already guessed it, where I want to get at. Of course, there is a data movement. There is a paper movement problem because you need to get the proper papers from the warehouse on the desks of the office workers. Luckily, we found an empty storage room where we can store some boxes of paperwork intermediately. And of course, we have some data movement accelerators available, some robots, and they are specialized depending on the type of room that they have to operate on. Big robots for the warehouse, very special one in the storage room at level 2. That guy can open boxes, take out paperwork, reshuffle it if needed. Maybe the paperwork was in historical order, you want in alphabetical order. That robot has a copy machine. Maybe you want to duplicate some paperwork before you send it off on those smaller robots. and then bring the dedicated paperwork to the worker that will perform the task. Okay, we're going to miniaturize this. We're going to bring this to a micro device level, and then it starts to look like a chip architecture. It's a spatial chip architecture where every component, every tile in this architecture can run and work concurrently. And you recognize already that we have the same levels here presented now in our memories like we had in the previous real-world example. Our set of workers are on top rows. Those are our compute tiles. They are equipped with AI engine cores. Those are VLIW vector processors. I'll come back to them in a little bit. And they can either communicate with their direct neighbors in the way like I described before. They can, with their physical neighbors, directly talk to them. The green part of those compute tiles is where the real computation will happen. And similar to my example of the real world, the only memory that they can see, the only memory that they can address is their own level 1 or the one that they can see, they can peek into from their direct physical neighbors. Now, every tile in this array can communicate with every other tile in this array. And it's a little bit different than really having robots flying around. What is happening actually is that we have this interconnect network that is connecting all of the tiles in this spatial architecture. And when you want to move data around, that is where the purple boxes in this drawing will be deployed. It's always a communication with the sender and the receiver, and we call them, we use half DMAs. At the sender side, you use half a DMA to fetch some data from the memory where it is at the level in the memory hierarchy. It puts it on that intercommunication axis stream network, and then the other half DMA at the receiving side picks it up and can write it into the proper memory depending on the memory hierarchy. For instance, for a compute tile, it would write it into the local memory so that then for that compute tile, for that worker, the data would be available that it wants to work on. You can see that this is a very spatial architecture. It's an architecture, I hope you figured it out by now, with explicit data movement. You need to configure the architecture in such a way that you bring the data to where it needs to be. The advantage of doing that way is that we can make a silicon efficient, but also a very energy efficient implementation because you can tailor the data movement to the needs of your workload. And since this architecture is so adaptable, is so configurable, you can implement different types of parallelism on it. Either you give multiple compute tiles a different task and you build a kind of data flow task level parallel pipeline. Or you can also, if you want to, give them all the same task, but then, for instance, use the broadcasting feature of the interconnect network that is there to duplicate data, if you want to, or if that would make sense, so that you get to a more data level parallel implementation, if that makes sense for your workload, and you can mix and match. I want to make sure that this can be, although we're pressed on time, it should be an interactive session. So any questions, please ask them while we're presenting. In that way, we can make sure that you're all still with us. We know the data movement in advance, right? Yes, we make an assumption. Well, there's two parts that I can give as an answer. What you would do for your workload is you would study the data movement patterns. So that would mean you know them in advance. You can analyze them at compile time, and then you can use that in your compiler stack to properly set up all of the data communication infrastructure. It doesn't stop there completely. I didn't yet talk about the lowest row on this drawing. Those are the shim DMAs. That's how we communicate with the external memory. That is typically, even in our current software stack, where we have a little bit more dynamic aspect, where the host can at runtime kind of start to reconfigure how the data is actually read from or stored back into the external memory. And the architecture itself has sufficient flexibility that during runtime, you can actually also reprogram the DMAs at every level. So you do not necessarily need to make all decisions up front from a hardware architecture point of view. Though, for completeness, our software stack currently mainly focuses on analyzing things statically at compile time.
And also each memory is a scratch pad, so again, each level.
Yeah, that's very important to realize. That's why we use the terminology explicit data movement. And that's why I mentioned now multiple times, a compute tile can only see and address its own memory. So you cannot say easily, I'm going to read data from L3 and then rely on a hardware backed up cache infrastructure. That is not how this architecture is built on purpose, right? We did that for silicon efficiency, energy efficiency reasons. You as a designer or through your compiler stack need to set up all of these data movement infrastructure to bring the data to the compute tile where it's needed in such a way that it exploits all of the capabilities of the architectures most efficiently. I seem to confuse you.
Yeah, I don't know.
It will become clear maybe later on as well, more clear in the presentation, and certainly also when Gagan showed some of the implementations we made, we will explicitly show how we are moving all of this data around. You also should not be totally scared about that. We, in our compiler stack, have built necessary data movement abstractions to make it easier to describe all of these spatial data movement configurations so that you don't have to program. If you want to, you can. Our compiler stack doesn't hide any detail, but if you want to, there are easier, more convenient means available to you to set up all of that explicit data movement. Yeah, and otherwise you will just ask more questions.
One other question is, so this whole thing is tailor-made for neural network inference?
So that is a very important application domain, exactly, but it can also do other regular types of signal processing. So it's a generic architecture as well, as long as they are not like overly random and overly sparse in a random way, so that you can properly express all of the communication that needs to happen at a granularity that this hardware supports. You can support any type of signal processing as long as the compute operations, of course, match with the type of vectorized operations we offer in the AIE core and the compute core itself. So yeah, so this hardware is available now. Gagan has a laptop on his table with Ryzen AI processors, first generation, it's Phoenix, and then we had Hawk Point. We recently released Strix. Ali will give a little bit more detail on Strix, why we are really stoked about that one from data type point of view. It's not only available in this product line, it's also available in the embedded space in the virtual product line, where we combine larger array sizes of AI engines with our programmable logic and a ARM CPU complex. Okay, hardware is only valuable anything if you can use it, if there's a software stack available for both the programmer. We did it in such a way, we are building on top of mlir, and we do that for the main reason that, first of all, we can easily continue to build off things that are already available in the open source. But secondly, we do not only want to enable the software developers, we also want to enable the tool developers so that they can extend our compiler stack with their variants or their extension tools by plugging into our mlir compiler stack, and then maybe be more domain specific for whatever application domain that they have in mind. So I will first give a little bit more details on the hardware architecture itself, and I will spend a few words on the tool stack, but I want to use that section mainly to kind of go a little bit into your question and to explain those more abstract communication data movement patterns that we support. Then Gagan will take over with Hello World, multiple examples, and then Ali will wrap it up with the data types. So we already talked about the compute tile itself. We have the compute core in green, the engine core itself. It has its own local memory, typically 32 or 64 kilobytes, depending on the generation that you're using. And then very importantly, because every single compute tile can perform its own dedicated specific task, it has its own program memory. And then the other important part is that you see that we have hardware locks. Hardware locks are there to be able, in an efficient way, to keep the different spatial tiles, compute tiles and memory tiles, to keep them all synchronized. A little bit more details on the compute core itself. It's a combination of a scalar unit, but then more importantly, the part that we really care about from compute density point of view, with the vector unit. In the vector unit, we have two types of data paths. There is the important MAC data path, where we really care about the compute density, and where the compute density itself is dependent on the data type of your operand. So if you look to the table on the right-hand side, for instance, on the second row, you would see that for an int-A data type, for both A and B inputs, you have 256 max per clock. If you go to a more precise data type, for instance, int32, you see that you only have 60 max per clock. So this is a VLIW vector processor, which means that you have multiple VLIW slots to make sure that multiple things can happen concurrently. So while you're doing a MAC, the compiler, the single kernel compiler, can also schedule a other vector operation, either shuffle, add, or compare. And at the same time, in other VLIW slots, you can, if needed for the application, you can schedule two load operations to load the data into the vector registers, and you can schedule one store operation. And I think we have another VLIW slot, not for a vector operation, but for scalar operations. Then the mem tile is a scratchpad memory of 512 kilobytes that you can use for intermediate storage. For instance, to store data where you want to use more or use something that is reused over multiple iterations of certain compute tiles, so to exploit data reuse. And then, of course, for every type of tile, we have the hardware logs to be able to keep everything working in a synchronized fashion in this spatial compute array. And then the final tile that I want to point out is the one that gives you access to the external memory, which is our shim DMA tile. This infrastructure allows you to implement different types of data movement patterns. I already highlighted at the beginning what you see on the top, which is a direct communication you can have between physically neighboring tiles. But then if you want to, because they're further away, they can also talk to each other, but then they have to go over the DMA axis stream interconnect connection. And then depending on your type of application, if you need data from the external memory, you can either choose to bring it in directly from the level 3 using the shim DMAs to the compute tile itself, or if it makes more sense, you can do some intermediate storage in L2, and then from there, with a reuse pattern, for instance, or a distribute pattern, you can bring the data to the compute tiles that need to operate on it. We already talked a lot about data movement. The capabilities of the DMAs at every type of tile in this architecture are a little bit different. You see in the table on the left-hand side that the most capable DMA is actually the DMA where we kind of share a larger amount of memory with different other tiles in the architecture, which is the mem tile. There we have more dimensions that we can use to program up the accessing. We also have a feature called zero padding, and we have more channels, more DMA channels available that allow you to put data on the axis stream interconnect network. Very briefly around the tools, I already mentioned that we are using mlir, multi-level intermediate representation, as vehicle to build our compiler open source tool stack. We do that mainly because it allows to kind of build towards, first of all, a hardware-specific backend at the bottom of the slide, where you can see on almost the right-hand side of the slide, you have our AI engine backend through our mlir-aie dialect. The reason why we like to use mlir is because in the middle part, you can actually pick from the different passes in this toolbox what makes sense to kind of lower your design gradually and apply the optimizations at the proper abstraction level. And then at the more front-end part, depending on which application domain you try to cover, you can plug in an engine for the proper ingestion into this whole tool stack so that you can cover different application domains in a more domain-specific way. We've built a prototype of an end-to-end stack using this technology. And in this example, if we start from the top, the application domain that we support is machine learning. So we can take in PyTorch, we take that into the framework, we convert it to a dialect called mlir lineage. Then we can lower it through the interface on this slide, which allows us to explore how you would tile up a problem, both in space and in time. but the focus today of this presentation is actually on the two lowest boxes of this drawing, is at the iron level. Iron is a close to metal toolbox for performance engineers to enable them to build designs on this architecture. And then for a single kernel, what we have is the piano compiler to compile your code for that one. The iron builds around the mlir-aie dialect. It's really meant for performance engineers. That's why I said before that we don't hide any detail in the architecture. Everything is available if you want to do so. But you will see from the examples that is very structural and very close to the metal, very low level. Gagan is already standing because I need to speed up. I'll skip over this. I do want to spend 2 minutes on how we simplify setting up of all of that data communication. And for that, we have a communication principle, which we call an object FIFO. So let's make the assumption that you want to communicate data from a source tile, wherever it would be in this array, to a destination tile, wherever it would be in this array. You can do that by using a communication primitive, which we call this object FIFO. And you have to specify what is this in the spatial configuration, what is the source tile, what is the destination tile. You have to specify the amount of elements, the amount of objects that you want to be able to hold in this circular object buffer. And then you also need, of course, to specify the object data type. And then this communication primitive for you will do everything from data allocation. It will allow you to get access to a single object to start to work on it through an acquire and release pattern. And then under the hood, when you lower this into something that you can run on the architecture, it will do everything for you on the spatial architecture to set up the DMAs and then to use that communication infrastructure to get the data from the source to the destination. Gagan, I will take the question and I will hand over to you.
Just taking a step back, what's the motivation for having both the ability for direct communication and also peer-to-peer with this packet switch network?
Right. So the reason why we add the peer-to-peer communication over the fact that we already connected any tile with any tile is that we can actually offer a higher bandwidth in the peer-to-peer communication. The second reason is that there are some resources in the end that are scarce on the architecture. You only have a limited amount, that was a table we had before, of DMA channels that you can use to put data on that communication network. In some of the application examples that Gagan will show, we actually run out of DMA channels, but we can still make our implementation because we can fall back towards that high bandwidth direct peer-to-peer communication. I'll skip over this because I tried to verbalize it already. I just want to point out one more thing, which is this one. So our DMAs, so all of the purple boxes I showed to you on this architecture slide before, every time you go through a DMA, you have the capability to do a data layout transformation on the fly, as shown on this graph over here. And how you have to read this line of code over here is from right to left. And you specify both a length of the operation. So for this row, for instance, we wanted to copy 3 data elements, but you specify a stride as well. A stride of 2 would mean you skip over 1 every time. And then you repeat, so you go to a higher dimension. You say, I have a length of 2. So you repeat the same operation that happened here a second time, but you told over here that you want to do that with a stride of 16. So you jump over 2 rows of 8 and you start to continue your operation from there. So it works with half DMA. So if you traverse the memory hierarchy, every time you go through half DMA, you have the possibility to do a data layout transformation like this, which is actually pretty powerful to make sure that by the time you land in the L1, you make sure that your data layout is the best for the vector instruction that you want to use. Thanks.
So let's talk about a bit of some real world examples. First, I'll start with a hello world example. First, you want to know about like how the compilation flow works. So we have 2 parts to it. First will be a source code, which will be like a normal C code, C++. And we use chess compiler or piano. Christo went a bit into that. So that one is for like a single core. And when you want to connect different cores together, then we use our Python bindings, and then together they generate Ryzen AI binaries, and that's the compilation flow on a high level looks like. And we'll go into like how a simple hello world vector example will look like on a platform. So assume that we have a vector operation where we want to multiply a vector A with a factor, which is a scalar, and you have a vector of 4K elements, and then we divide it into sub-elements of like 1K. And the C code will look like a normal, like the AI code is quite similar to C++. And this version is for the scalar operations, so it will run on the scalar core. And now if we want to implement like the data movement, what Christoph was mentioning about it before, so we have to think about like how the data movement will happen for different vectors. So first is the input vector, which is the A vector. We need to somehow move the data from the external memory using the shim DMA and then push it to the core, which we are using. In this case, we are using the first core. And you see, we are not really going through the mem tile here, so we can skip it. So you can do the connection the way you would like to. So if you want, if needed, you can even go through the mem tile. If not, you can directly skip it. So you will first read A data from the external memory, you push it onto the stream, interconnect using a shim DMA. And once you have it on the shim DMA, you can pull, the core can simply pull data using the half DMA. And now you perform a vector operation or a scalar operation, depending on what core you're using. And once you're done with the computation, you need to configure it back, the data. So the C vector, which will be, again, you need to put the data onto the axis stream. Then you pull the data using the shim DMA, and then you write it back to the DDR. So if you look into like how the Python binding would look like for these, so this one is the code which will run on the core. This is the scalar version. And to connect all the data movement, we use Python binding. It's quite similar to how you would write on a Python level, so it's a bit natural how you would do things. So first you declare the function. Here we say like scale in 32, then you instantiate the tiles which you're using. So we call each of these as tiles, each of these blocks. So if we are instantiating a shim tile, we call it like, we provide the coordinates for those. So it's 0, 0 in this case, so the bottom row of it. Then we instantiate the compute tile, so which tile will perform the computation. And like Krista was, like he briefly mentioned and he skipped quite, we didn't have the time to go in detail. So there are these object FIFOs, which encapsulate all the data movement, the data access, data allocation, and setting up of locks and stuff. Everything has happened using object FIFOs. So we instantiate these two FIFOs, which is FIFOs for in and out. So for which represent the input of the vector and output once you are done with the calculations. And then you can provide the depth, you provide the data types and how the computation should be performed. And here you provide all the communication and how you will access the elements for the computation to be run on the core. So for example, here you see like we acquire one element from the output object FIFO for production, so it will produce the data. And then we have another object FIFO which will consume the data. So this one is the A FIFO, object FIFO for the input element. And then we pass these FIFOs to our function. And simply then once we are done with these use of these object FIFOs, we can release those. And also like how Krista was mentioning, we also need to set up like the external communication. So we have this runtime sequence where you define like how much of data movement needs to happen from the external memory. So you define like, so for the A element, this is the amount of data you will move, which is 4,000 elements. And for the C as well, you have 4,000 elements. So that's how like the Python binding looks like. And it's quite natural, the things which are done. And if you have any questions, just stop me in between because I have to quickly rush through everything. And I think Christoph briefly mentioned we have tracing infrastructure as well to measure the performance and to analyze like where the bottleneck lies. And also one more thing, all these examples are implemented and they're open source and available on our website, so you can go through it and have a look. So there's tracing infrastructure here where you can figure out like how the code is running, how the data movement is happening when the logs are set up, so that you can figure out like if there are some bottlenecks and how you can improve your code further. So here we have a scalar version, so it performs really bad. So it's take like 10,000 cycles, from the beginning of the event to the end of the event. But still there's concurrent data movement happening. Like Christoph was mentioning, there's all these mem tiles and all these cores, everything can happen concurrently. So nothing has to wait for the other part. So the data movement is happening in concurrent with the processor. And once the processor is available to release, when it produces the output, it can send out the data again on the axis stream, and then you see the movement happening here again. So this is like a bit of how the tracing looks like. So if you make a vectorized version of the code, so for vectorizing, you will have to use intrinsics. So there are like some pre-defined intrinsics we have for different vector operations. So for loading the data, for performing vector MAC operations, vector additions. So if you do using those intrinsics, then you see the performance is way better. You have 600 cycle, which makes sense because you're vectorizing everything. And now we have like back-to-back data transfer with computation. So whenever you keep the data is ready, you keep on loading it. So everything is happening concurrently. So this was like a really simple hello world example. So let's go into like some more real world use cases. For example, this one is edge detect. One thing I would like to mention is this AI engines consume really low power. It's almost like a few watts of power. So if you have a complete edge detect pipeline and you would like to implement and run it on your AI engines, we saw like we can get almost like less than 1 watt of power consumption, and you can increase the kernel rate compared to if you're running it on the CPU of this Ryzen laptop, which I was showing. So if we talk about like implementation of this pipeline, it's a bit more complex than the previous one. But here is the complete pipeline, how it looks like. We have 4 different kernels, and then there could be a skip connection from the beginning till the end. And if you want to implement such a kind of workload, how would it look like? So on the right, we have this schematic of this Phoenix device, which I showed before. And the device is divided into columns. So there are several columns of AI engine. And if we suppose we just want to use like one column to implement such a complete pipeline, how would it look like? So the colors here correlate with the colors in the kernel, and we show it here. So you have the first kernel, which is implemented on the second tile of the AI engine architecture. And then there's the third one, the second kernel is on the third tile, then 4 and 5th. And then we need to set up the data movement around it. So again, like the way I was showing these Python bindings before, we instantiate the shim tile, we call the mem tile you want to use here. Then you have all the core tiles, you provide the coordinates based on where you would map the computation. Then you again set up these the FIFOs. In this case, there's a bit of special scenario that we are passing through the mem tile because we would like to perform this skip connection in a later part of the pipeline. So you take a deeper FIFO, you allocate the FIFO in the mem tile, and the later part you feed that FIFO into another core. So that's what we do. We have the input, which we broadcast. So that's one of the things you can do with this architecture. You can broadcast the same data to multiple cores or multiple tiles, I would say. So here we are broadcasting to 2 tiles. One is the mem tile, the other one is the final tile for performing the skip addition. Then you just link them together. So there's this syntax for that. And same way, like on the output side, so you perform like a data flow execution. So you send the input activation once. You work on a part of the tensor, you send the input activation once, and then you don't really send any intermediate results out. And following which all the cores are working on a part of the tensor, and only once you're done with the final output, you send it out from the shim DMA, and that's what we do. And then these are like this in between compute tiles, intermediate FIFOs between each of these tiles. So you can set up here, and then you can provide the depth based on like how much computation there is. So you can set the different depth for each of the FIFOs. So that's how it looks like. So this is another example which we have implemented, and it's, yeah, go ahead. Sorry?
What's the reason for
No reason. We just chose it to do it this way, like one column. But you can use everything. You can use every part. And I have like one example after this one where we are using multiple columns. And you don't really have to do it like in a data flow way as well, like we do it. But in the end, the goal of this architecture is to go as little as off chip as possible. So that's why we implement it this way. But you can do like, I don't know, layer by layer approach as well, where you're using one layer across all the cores as well. So whichever way you want to. So there's a lot of flexibility.
And you can spatially look at one grid, one application.
Yeah. 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 Yeah, that's a good question because, okay, so we have per core, we have 2 channels. And then if you think like, if we are getting like one connection from the core 4 and we are getting one from the 5, and for some reason you need to send like, in the next case, I'll show that you have to send the weights as well. So you're already out of your number of channels which are there. So in this case, what we try to do is, like Christoph mentioned, you can use shared memory. So when you use shared memory of the neighboring core, you don't really go through DMA. So you have a direct access to the neighbor. And in that case, you don't really use the channel, and then we can do the skip connection in that case. So you have to play around with the placement as well of how the core is. And if you have even more complex scenarios, then this placement even becomes even more important to take into account.
So channel is overload technology. DMAs have DMA channels. So you have DMA input channels, DMA output channels. And then you put it on an access to interconnect. And then now the technology is not good because
right.
We also use the channel for how many channels you have on the access. Yeah. So those channels in the network, you can get it two ways. Either, I didn't explain it, but there are switch boxes in the interconnect network. You can use a circuit switch mode in which you kind of directly set up communication from one point to another. You have like on average 4 channels, one direction, other direction.
Yeah.
4 channels. So you can run out in the end as well. It's not game over because you can also use communication. So either you as a designer or the tool can decide. Or a combination. Yes.
Mm-hmm.
So is this mapping as a user? So in the example that Gagan is describing, he was
so I'm the yeah.
Point because we want to build examples where we show the best use of the architecture. Now we of course are working on compiler technology. That's also why we have a compiler stack, the open source, where the tool can make more and more decisions. I don't want to steal the show. So
No. Yeah, like design space is really important, especially in this case, because there are so many cores. And here we are just showing you like a 20 core design, which is actually out there, but still like there are like some other variants of AI engine where there are 400 cores or even more. So it becomes pretty like design space exploration is really important now. Right. Right. Yeah. So yeah, we are looking into design space exploration as well. It's really important. Oh, well. Okay, so another use case is this resonant. Everyone knows it's like a quite famous computer vision network, and there's several bottleneck layers. If I talk about this meat of it, it's residual blocks or bottleneck blocks. And if you look at a simple block, it has a 1x1 convolution followed by batch norm and ReLU, and then 3x3 and 1x1. And there could be a skip connection or not, depending on where you are in the architecture. So we can fuse the convolution and batch norm. We know it's a runtime optimization, which you can apply. And in AI engines, there are like some tricks we can play. For example, is like we can absorb the ReLU as well by means of the shift round saturate, which I cannot go in the detail, but it's a hardware unit where once you're done with the accumulation, you need to send your results out into like certain precision where you can clip off, you can saturate the way you would like to. So ReLU can be absorbed. So in the end, you're kind of left with these 3 kernels. And again, if we start with like mapping of how it would be, it kind of, if you see, it's kind of similar to what we already mapped before for the previous design. And now if we have to map this block onto the one column, again, I'm talking about one column just to make things easier. So you can map like the first core on a single AIE core, then the second core has more computation, it has more amounts of weights. So you can split it across div 2 cores. And then for the final one, again, you can map it on the remaining 1 core because still we are assuming that we have 1 column. And now, like Christoph was mentioning, like we have to somehow, there are limited channels which are coming from different levels. So shim has lesser channels than memtile. So what we do in this case is we exploit the memtile to distribute the weights. So it's kind of like sending all the weights to each of the different respective cores. So because it has more channels, so we can do that. And then for the activation, we again send it once, and then we get it out for the final skip, final output once we perform the final skip addition, which is again, we use this memtile for doing the skip addition. So this is another example which we have implemented, and it's open source as well. Okay, I wouldn't go into details of how we write the code, but everything is there, and you can have a look. So this was like one bottleneck block, which we were using single column. And like I was mentioning, there are like several layers of bottleneck blocks there in the ResNet. So we can easily stack these with one and chain them together. So one output of one bottleneck becomes the input for the next one. So we did that in this design where we're using like 2 columns. Then you can do 3 columns, 4 columns, same way like 5 columns. So you can have like full design on the allocated cores which we have available here. So you can do that. And it's also in open source. Another use case, so like there was a question before, like about, is it just for ML? No, we also tried out like different application domains. So one example is weather stencil, which was done on the previous generation of AI engine. So it was AI engine 1, where we made a design, we stamped it out to 384 cores. And like we were discussing, the design space was even huge. We published it in ICS, and we showed like you can get really good performance if you can with this AI engine cores, and it's really efficient as well if you do that. Another use case which I'll flash is about genomics. So base calling is, I think, quite a few people work on genomics, so they will understand it's like the first step in genome sequencing, where you have this analog signal and you translate it into ACGT base pairs. So you have this DNA, you have this, you use base caller for that part. And then we published a work this year, actually, it's called Rubicon, where we made a framework for designing efficient deep learning-based base caller. So in this work, we were taking into account really about like all the different data types which are present and how you can exploit that to come up with the efficient deep learning-based base callers. So Ali will go into the details of that in the following slide. But before I leave, I just want to tell you like how you can optimize for AI engines. So always think about data reuse, so which is like normal, since we know it's like we don't want to go off chip. Think about data locality. You might have to rearrange data so that you can exploit like how the compute happens. Think about load max store. So we have the VLIW architecture, so you want to make sure that you fill up all the slots as possible. Then always try to exploit as much of vector data path. And then there are like MAC units, which are optimized for matrix multiplication. Take into account the data type precision, which Ali will go into the details of that. And then I was talking about the example of we can exploit existing hardware features as well, like I did for absorbing ReLU. So think about all the features which are there whenever you're trying to optimize this. And I think now Ali will go into details of like how you can exploit the compute density which is available.
Thank you. All right. Hopefully, I can go through all of my slides, but there is one other dimension in this AI engines, and that's data types, data formats. The data path in the vector units can support, this is for the first version of AI engines, and it can support those combinations, precision 1, precision 2. You can think of activations and weight matrix. One of them can be precision 1, the other one can be precision 2. Any combination is supported for AIE version 1, and for future versions, AIE version 2 is already out there. We are supporting different and more data formats. I'm going to explain why we are doing that, and also what we like to achieve. There's a loop between hardware and applications that we like to make it a little stronger, so these data formats can get out there and be used in a way we like. I have to go through a couple of slides to put some meaning behind what I said. The first part of that loop is the trend in AI. One of the big application domains out there. I put the title of the as a title of the slide or accumulative AI knowledge, meaning everybody in the world, not just us, AMD. The current trend shows we need more compute, more parameters, and larger data sets in order to make powerful models. In particular, for neural language processing. So this is not super good, but this is what it is for now. If you look out there, all of those models, those groundbreaking models, those famous models, they are getting bigger and bigger. So it costs a lot to train them. You need a lot of compute power, and you need more time, expertise, etc., so on and so forth. One part of it is the cost of operation, data movement, and doing the computation. On the right side, I'm trying to capture the differences between the amount of energy and the number of bits you use to encode your information. 8, 16, 32. It doesn't have all of the variation of the data formats, but you can easily see a pattern that larger the number of bits, it costs more to move the data. You already know it, but besides the cost of compute, those data formats, they have different characteristics, which is dynamic range and precision. I'm going to go through a very simple example to show you why it is important, specifically for AI engines. And before going to that example, I'd like to bring up to your attention that the data formats that are out there, well, there are a lot of them, but FP64, 32, bfloat16, and float16, they are already popular, meaning you can already download models in those data formats. You can already run them on processors that they support these data formats. In 2022, OCP supported FP8. A bunch of companies, including us, we got together and said, hey, let's standardize it regarding what to support for rounding modes and etc. FP8 is not a new data type, but it's a new data type that is supported in many hardwares. Last year, OCP came up with MX data type. This is a block scaled data format. int8, FP4, FP6, and FP8 are the data formats for each value, and then a block of those values share a scale. That's why they're called block scaled data formats. And we also support a little more of those data types that are not part of the OCP. There are MX694 and also BFP16. I'm going to use this BFP16 in my example to bring up to our attention that why these block scale data formats are interesting, although they are not easy to package because you have uncomfortable number of bits per value. So BFP16, for example, has 8 bits per value, and then you have 8 bits of exponent that is shared between 8 values. So you're going to make like 9 bits per value. So moving it around, data layout, they get very complex. So for the example, I have a distribution D. I'm going to take samples, put in matrix A and W, multiply, and create my output. I'm going to cast A and W into 2 other matrices that are quantized values, just casting, nothing else. Calculate my output and figure out what's my peak signal to noise ratio. I'm going to use those data types. Those data types on the right side, they are choose because the bfloat16, int8, and BFP16, they have 7-bit for mantissa. So precision-wise, they're very similar. int16 has almost double of that, and int4 has, well, that should be 3, not 4. int4 has half of that. So I want to show you what's going to happen if I play with that exponent, share that exponent in BF16 versus BFP16 versus not having the exponent in int8 or int16. So here, the yellow line shows my PSNR if my distribution is a normal distribution. So imagine a normal distribution, not much dynamic range, mean 0, standard deviation 1, precision is much more important. So int 16, the second from the second point from the right side, has a high signal to noise ratio, but bfloat 16 doesn't have that much. And the rest of the data formats, they are lower. If I change my distribution to uniform, it is still not much of a dynamic range. It's between 0 and 1. And int 16 is still good, but because of the dynamic range, you can see the difference between having you can see that the effect of that exponent in int 16. That's kind of visible. But if I go to exponential distribution, which has a larger dynamic range, you can definitely see my signal to noise ratio for BFP 16 has a tiny bump, but for int 16 has a big drop. In this particular example, BFP 16 is outperforming int 16 for PSNR metric. I'm going to pause if there is any question, and I'm going to add that BFP 16 has the computational density of int 8. So in your data path, you have int 8 values, you multiply, accumulate, at the end, you just use that shared exponent, which is a power of 2, you shift left and right. That's it. So you add a little bit of real estate into your hardware, and also move a tiny bit more data per value, but you get that bump into your PSNR. So BFP 16 is known as a casting data type, meaning if you quantize your values with BFP 16, you pretty much don't need post-training quantization error training. You don't need any of those. You just cast it. But if you go to lower precision, you need some algorithm to get rid of the quantization noise. If you go to a real life example, those distributions are not normal, uniform, or exponential. They are more complex. That cartoonish curvature just shows it's trying to capture the complexity of those distributions for your activations, for your weights. You have outliers depending on your applications. Your application can be image classification, object detection, LLMs. You have different model architectures that's depending on the size, depending on the number of parameters, they can be in a narrower or wider local optima. So when you quantize them, changes in your values may translate into more dramatic or less dramatic changes in your quality of your model. Therefore, we should support multiple data formats in order to cover a larger set of applications, so the hardware can be more generic. So this is the second trend I'd like to bring up here. This is the support in academia, in tech companies, in open source landscape, that everybody is thinking about reducing the cost. We are also supporting the cost by releasing pre-trained models that are already quantized. Our hardware is trying to support more and more data formats. And we are also publishing open source libraries in order for you to go and get your hands dirty and play around with these data formats. The goal is to have these data formats out there. So the data scientists, the ML folks, the people who are trying to design those models get comfortable with this hardware, and hopefully adjust their hyperparameters in a way that their model work with the smaller or narrower data types. I can continue, right? Okay, excellent. Thank you. I'm going to go a little faster. The TensorCast library is available on GitHub. It's a BYOD, bring your own data type. You can define your data type, the size of the block, the shape, it is 2D, 1D, whatever. The type of your shared scalar. Do you want to share the scalar? You don't want it. The type of each private value, FP, int, you name it. It's kind of easy to use. You have to define your algorithm, but you can pass a dictionary and say, this layer, I want this data type for my weight, that data type for my input, output, etc., and quantize and play around with those data types. And using the compiler that Christoph and Gagan mentioned, you can hopefully compile and run your model on your devices with the data type that the device supports. We also, all right. Apologies for going fast, but I have to. We also published error diffusion. It's available on archive. This is a PTQ method for supporting the block data formats. There's an orthogonality between the dimension of that block, the contiguous values that share one scalar, and the way usually PTQ algorithms diffuse the error. So because of that orthogonality, we had to make some changes. I'm going to go to the next slide. These are the results of that paper. And I'm trying to make the point, you can go back and check it later, but I'm trying to make the point that when you get to the smaller data types, it gets challenging for PTQ, then you have to go QAT, and there is a dependency between the data type you use, the model size, the data complexity, which is the data set complexity, what's the distance between your discriminating features, and what's the task, and so on and so forth. The next slide has a very important message, which is the complexity of quantizing well-trained model. The models that are being published year after year, they are getting better and better, meaning they're harder to quantize. I'm going to just go briefly between these two. This is Hugging Face. We download the model, we fine-tune it for Wikitext2. The fine-tune model, which works better for this particular data type, is harder to quantize. When we quantize it with the same method, we get worse results, 98% of the baseline versus 99% of the baseline. And everything here is there to make the point that mixed precision is extremely important. Using different data types per layer. I'm going to go to my last slide because I have to. And with mixed precision, this is the Rubicon paper. I want to point out that accuracy, there is pretty much no drop. Number of parameters is cut to half, and model size is 1/6 because of using mixed precision and only the combination of these data types. So this is for AIE1. Now we are supporting more and more data types. You have more flexibility to play around and even reducing these even further. And with that, I'm going to jump to the very last slide, and I'm going to stop here. Questions? That was which GPU did we use for the ProxyNAS? MI210. Yeah, one device. Yeah, one device. And the space was large. The data set was also truncated, so 140 hours. Yeah. But that's the one-time cost. After that, inference going to be multiple times lower cost.
This is the very last question. There is another lecture from that. Oh, okay. You talked about long-range models. Does that run on these low power?
Yeah. We have Llama CPP.
So
yeah.
AI engines are really optimized for that.
Yeah. Yeah. Yeah.
Within limitations.
Yeah.
The amount of compute that the output can offer, that's what.
Yeah. The goal is to run it on your laptop without draining your battery, with no fan. Yeah. Yeah. All right.
So we have one tradition before you run away. If that's okay with all of you, we would like to make a selfie.